So in the previous video, we actually derived our force 1 and force 2. Okay, now we're gonna put them into matrix, and eventually we'll get our F equals to KU already at this particular video. Alright, and as you can see that it's B1 times B1 U1 times B2 U2, so you have like a B1 square. Alright, things like that. So I'll just bring all this stuff, just crop this, paste it over here. Okay, so we have a B1 B1, so B1 B1 is this one, and then this B1 will also multiply into B2 U2, so it's B1 B2 over here. Well, for this case, B2 B1 is over here, so I'll just simply sub in as B2 B1 over here, while the B2 will multiply with B2 over here, so we have a B2 B2 over here. Alright, simply subbing in the stuff. I think this is pretty much straightforward for you. It's just the matrices only. And as you can see, you're starting to see something like sigma 1 1, sigma 1 2, sigma 2 1, sigma 2 2 type of thing. Alright, but this is not stresses. This is just some EA over L type of stuff. Alright, so at least you can see that it's 1 1 1 2 2 1 and 2 2. Okay, once you see this form over here, most likely you can say that this is a dyadic tensor. Alright, it's a dyadic tensor product, because the dyadic tensor product tells you something like 1 1 1 1. Okay, or in other words, 1 0 0 0 plus 0 1 0 0 plus 0 0 1 0 plus 0 0 0 1. This is the dyadic tensor type of explanations, if you want to say. Alright, so this whole thing over here can be rearranged into here, stating as B dyadic B, and that's all. Okay, and most likely you will have some form of I'll leave it there first, but I just want to show you that B in this case is B1 and B2, so it's somewhat like B1 B2 B1 B2, or in other words, if you were to write it in terms of a dyadic tensor form, is B1 1 B2. Okay, so if you were to multiply, you'll have this form over here. So this is something of a short form to rewrite your stuff. Okay, and therefore once you get this is your somewhat near to our answer already. While your B is equals to your B1 over B2, your Fi is equals to your F1 over F1 and F2, and then your U is simply your U1 and U2. Okay, now I'm gonna bring this E over to this side. Okay, I'm gonna bring this UV at the behind. I don't know why they want to do that, but I get what it means already. Alright, so you bring this E to this side, you bring this U over the other side. Later on you'll know what I mean. So therefore what I have is B times dyadic E times BT. Alright, as you can see, if I were to bring this E towards the side. Okay, so this thing over here actually multiply by dV also lah. So never mind, I'll manually do it for you. Alright, I'll just bring this thing, I'm gonna bring it over here. Alright, and I'm gonna bring this stuff over here. Okay, yeah, okay, so therefore this thing over here is simply the same as this thing. You can double check now. Okay, your Ui is equals to your Ui over here, Fi is equals to Fi over here, and therefore this is our equation. This is your F is equals to KU. This whole thing over here is your K, telling you the informations of your shape functions, the strain displacement matrices. So it tells you how the changes of your strain, how your changes of your, maybe you have this cube over here. Alright, maybe you're taking this small little cube over here, small volume dV, and then you see how this small little cube change its shapes. Maybe it may change something like this. Alright, and then you integrate throughout the whole cube, throughout the whole volume. As you can see, it's integrating throughout the whole volume. So this whole equation tells you that how the whole shape is being changed. So this is a very key information to tell you how the shape is being changed. Alright, give you the element of how the shape will be changed, and with relevance to how the input displacement is going to deal with it. Alright, if you input a certain forces, alright, with a certain constitutive equations of the material, how the material behave, you have you have the a different displacement. Nonetheless, if you can sub in on displacement, you will determine your forces. Alright, so this is some form of a very general equation, and it's a very powerful general equations to deal with other shapes later on. So in terms of other shapes later on, because currently what we're doing now is something like a triangular. Later on we're going to deal with in terms of a quadrilateral stuff or things like that. So therefore later on I believe we may still be seeing this equation again. Alright, so that's why I think this is a very general equation for your weak form for your stuff. And we call this the constitutive equation F equals to KU. Or in other words, this thing over here is your K, and yeah, I think we have derived all this already. Just to recap everything is that I took the strong form, I multiplied W, and then I introduced a U approximate, and then we know that has some residual values, and I integrate our some sort of this function, and then rearrange using integration by parts. Eventually we have something like this, right? And then after that we introduce the Calican's method in the previous video as a shape functions, so the W eventually becomes N1 and N1, which is when you sub in your W as N1. You can also sub in your W as N2, so we have a different shapes already. Alright, so these shape functions in relevance to that shape divided by dx will also give you a strain displacement telling you how the shape is being changed. So with all these understandings we derive the force 1 and force 2, telling us how the forces is being formed due to the changes of the shapes and things like that. Alright, and in our video currently right now we just simply mix the F1 and F2 together, sort things out a little bit to make things more clearer, to show you and illustrate to you that F is equals to KU. So we just simply rearrange to some dyadic tensors, product integrations, operations, things like that. Not integration but rather than but anyway, you get this thing over here, and I believe this is pretty cool, and yeah, this is this thing over here. And therefore in the next video onwards, we're going to use this equation to derive our EA over L. Alright, so I want to prove to you that there is EA over L over here. And I believe in the next lesson onwards, maybe not next lesson, but yeah, anyway, so in the next video I'll derive EA over L. And in the way future, you'll get to see that instead of EA over L, you're going to derive another form of stiffness matrix for other shapes. So therefore I'll just stop here first, and then I'll introduce certain stuff, and then later on we'll derive EA over L. And therefore, good luck. See you there.